All right, Corona video number 13, talking about electricity today, focusing in on circuits, actually introduction to circuits, here at BHS, the Rutgers of the MVL. So what we're going to be talking about today is some of the basic parts of a circuit, basically helping you with the top part of your problem set and then also getting you ready for your PhET lab. So let's start with the basic components of a circuit. Let's begin with a battery. So we all know the batteries come in different types. You can have a 9 volt, a 6 volt, a 1.5 volt. We have different sizes. We call them A, AA, AAA, B, and C. But all of them have a positive terminal and a negative terminal. Now, if it's one of these cylinder batteries, the protrusion will always tell you the positive. How do we represent this in something called a schematic? So when physics types are working on stuff, they don't take the time to draw out the battery. They just represent it with what we call a schematic. So a schematic would have two lines, and we would say that the longer of the two lines is positive and the shorter of the two lines is negative. And then it's a lot quicker to draw this and easier to work with. And so that would be our representation for a battery. This goes back to the original battery. The original battery ever made was called a voltaic pile, and we had alternating layers of metal with a conductor in between. And the conductor they started using at the beginning, believe it or not, was felt like the top of a pool table, soaked in salt water. And then they would alternate metals like zinc and silver, I believe, was in the original voltaic pile. And they just kind of made this kind of like Oreo shape. And when they were all done layering up their metals, they would take these two ends of the battery and they could do it different things with it, like shock things. For example, they would cut off frog legs and they would put the two terminals on the legs and the frog would kind of jump up or down or move. And it was kind of this weird kind of thing and that's where kind of Frankenstein comes from, if you think about it. Frankenstein is you're using electricity to recreate uh, artificial life and things like that. So that's where that's coming from. Another key component of a circuit is called a light bulb. Now, if you take the time to carefully look at a light bulb, you'll see that we have two pieces that are soldered, one here and one here. You can look for those soldering marks. And the wires come up into something called a filament, and then they come back down to the bottom where they're going to resolder. So how do we represent this in the schematic? How's this physics type going to draw this kind of thing? They're going to draw a little curlicue and then put a circle on the outside. And the curlicue is referring to that filament. Now this is going to be really important when it comes time for you guys to draw and work in the PhET. You've got to connect both sides of the light bulb. If you try to hook wires to each end of the collar, it will not make the light bulb glow. You must connect the side and the bottom, and that's why we have these two markers here in our representation. Now, anything that stops the flow of electricity, anything that will cause the current to make it difficult to move through this part of the circuit, we can also represent with this symbol called a resistor. So things like toasters or microwaves or fans or blenders, all of these things are considered resistors. And so light bulbs is a great example of a resistor, and that's what we're going to use to help us understand, because the brighter a light bulb is, the more current that is flowing through the light bulb. The only other symbol we've really got to deal with here at the beginning is the idea of a wire. Now, the wires we typically use will have clips on the end. So we can just represent a wire with a straight line. It's very easy to represent a wire. The wires that we'll use will be considered ideal. What does it mean to be ideal? When you're ideal, you actually have no resistance. So the resistance of our wires that we'll use will have 0 ohms. It's kind of like earlier this year when we ignored gravity. So we didn't ignore gravity. We ignored air friction, and that made life easy. Having a resistance-less wire, a resistance of 0, makes life very easy. It turns out that the gauge of the wire, how thick the wire is, can really affect things. The thicker the wire, the less resistance it has, actually. But we're not going to get into that. We're going to make life easy on ourselves. All right, so these once again are called pictorials, and these are schematics, and they're not the same thing, okay? Pictorials will help you see it, and the schematic is how physics types will kind of represent it. Let's begin by looking at the simplest circuit you could possibly have, and that's going to involve having a battery. So here we have a battery, and we're going to take wire and we're going to connect it down into one light bulb like this, and then we're going to take it back up to the battery. I'm going to go ahead and tell you some information. One, the wires connecting to the light bulb have no resistance. Two, the battery we're going to use, let's just use a 6-volt battery, a flashlight battery. So that's one bit of information, the voltage of the battery. So there's a number of things we're going to have to find. We're going to have to find the current in the wire. We're going to have to find the current in the light bulb. And we're going to have to find all these things, okay? And I'm going to tell you that this light bulb has a certain amount of current going through it. Let's just say that we have 400 milliamps. So if I said 400 milliamps, that's typically how we express current, because an amp of current would be a whole lot of current. That'd be about 0.4 amps. 400 milliamps, 0.4 amps, 4/10 of an amp. Okay, so I'm going to give you that information. I'm going to ask you to find the voltage in the wires and the voltage down here in the light bulb. I also want to know the current up here. Sorry, running out of room. The current in the battery. And I would also like to know what the resistance is here for the light bulb. Now, before we get into solving for these different things, I want to talk a little bit about current and the flow. So I told you we had a 400 milliamp circuit here. Scientists know now that electrons will originate here at the negative terminal of the battery and flow through the wire into the light bulb, go up into the filament, leave, and then come back here to the positive terminal. So that's what's really happening in a circuit, is we have the flow in that direction. But for a long time, before we discovered the electron, scientists thought that it was positive flow. And they thought it would start at the positive terminal and work its way through the filament and then come over here. And you know what? It works fine if you work in positive flow. There are many electricians that still think about things as being hot and neutral. And so that's called conventional current, CC, conventional current. The reason they thought this is because there was no evidence to contradict it until they discovered the electron. See, we had lights and we were using electricity to light houses and things like that way before we discovered the electron. So we were kind of using electricity before we knew what it was. Okay, so that's the difference between these two types of things. Now, when I say the current is 0.4 amps, what I'm really saying is that we have 0.4 coulombs every second moving through every part of the circuit. See, when you have a series circuit, that's what we have here, a series circuit, the current will be the same everywhere because there's only one way to get back to the battery. So series circuit means we have one path back to the battery. So we start at the negative terminal and there's only one way to get back to the battery. This concept of a coulomb is the SI unit of charge. SI unit of charge. So for example, like a lightning bolt would have a whole number of coulombs. Electricity in a circuit like this, less than a whole number. 1 coulomb is a crazy amount of charge. Usually when you like rub a balloon on your head and it gets charged, we're talking about microcoulombs. So when I say everywhere in the circuit has 0.4 coulombs per second, we can then take that and we can figure out how many electrons per second it would have. So another way to represent amperage would be coulombs per second, but we can also convert it into electrons per second. So electrons, which are very small, have this many coulombs, 1.6 times 10 to the negative 19 coulombs. That's not very much, right? But remember, a coulomb is a lot of charge and an electron is very small. So we can actually do some dimensional analysis and we can convert from this to this pretty easily. So if I say 0.4 coulombs per second, and then I use this relationship that I just told you, 1.6 times 10 to the negative 19 coulombs are 1 electron. If we divide this, it will tell me how many electrons pass through this circuit every second. So 0.4 divided by 1.6 e negative 19 gives me a large number, 2.5 times 10 to the 18. 2.5 times 10 to the 18 electrons per second is how many are flowing through the circuit. And so we end up with something like this. So when I say 400 milliamps, I could also say 0.4 amps. I could also say 0.4 coulombs per second, or I could say 2.5 times 10 to the 18 electrons per second. So when you start thinking about this in terms of electrons, it starts to get kind of crazy real quick. Now, to really understand how to find all these missing parts to our circuit that we have here, we've got to go through and use something called Ohm's law, probably the most important equation we're going to deal with here. So Ohm's law is V equals I times R, where V is voltage, I is current, and R is resistance. Now, voltage is measured in something called a volt. A volt is a ratio of energy per charge. It's a joule per coulomb. It's the push. It's like if we had a water spigot, it'd be how wide open you open the spigot. It's the pressure. Current is the flow. It's measured in amps. So we have volts, we have amps, and then we have something called ohms. So ohms tell us resistance. Voltage, current, resistance, and it gives us a measurement of how much it stops the flow. So think of a constriction and how hard it would be for water in a hose. If you take your hose and you kink it, right? How hard would it be for the water to get through that hose? That's what resistance is all about. So we're going to use Ohm's law and we're going to kind of find the missing parts of the circuit. Let's start with realizing, since this is a series circuit, everywhere we go, we'll have 0.4 amps. 0.4, 0.4, 0.4. Series circuit, same current. Everywhere in the circuit is 0.4. If you didn't realize that, then you would never be able to finish up the problem. Here's another thing. These wires have zero resistance. 0 ohms. That means it takes no push from the battery to get through it. Therefore, we have 0 volts. 0 volts, 0 resistance. That leaves us then with the 1 light bulb. So this battery, all of the push created by the battery, all of the desire for the electrons to want to go from one metal to the next, 6 volts, will be used to push the electrons through the light bulb. So this will get 6 volts. Now we can use Ohm's law finally. So I can put in my current here, and I can put in my voltage here, and then I can solve for this, the resistance. So when I take 6 and divide by 0.4, I get 15. So this light bulb has a resistance of 15 ohms. Okay, now you might be thinking, why don't they just tell us the resistance when we buy a light bulb? Because usually when we talk about light bulbs and how bright they'll be, we talk about it relative to something called power. So we talked about power earlier this year when we talked about the rate of work. Power is measured in something called wattage or watts. And then here we have our current, amps, and here we have our voltage, volts. So for this light bulb, if I put in my volts, 6, and I put in my amps, 0.4, I can get the wattage. So 2.4 would be the wattage of the light bulb. So the wattage created by the battery would be 2.4, and the wattage dissipated by the light bulb would also be 2.4. Now, the higher the wattage is, the brighter the bulb would glow. So if we wanted to make this bulb glow brighter, we could change our factors coming into here Maybe we get a different resistance and we'll get a different amount of glow. We could also use a different push. We could up the battery's voltage and we could make it glow brighter as well. Or maybe we give the wires resistance. If we give the wires resistance, then the bulb wouldn't glow as much that way as well. Okay, so all these factors kind of work together. It's kind of tricky to understand it. Probably the best analogy I've heard to help understand Ohm's law is this concept of a pump. So maybe you've been to like a park, like Charleston Falls or something, and then you've seen like a hand pump. So a hand pump has a lever, and then it's got a spigot here, and you move the pump up and down. Well, that's like the voltage, because we can control that. The faster we pump the pump, the higher the voltage would be. And then the water comes streaming out. Maybe we connect it to a hose or something like that, right? And then the water will come streaming out. Well, that's like the current. Okay, that's the flow. That's the electrons per second, or here, the water molecules per second. So that's the current. And then what we could do is maybe we would kink the hose or put the hose through a constriction, make the diameter of the hose smaller. That'd be like resistance as we kink the hose, and they all work together. Current, voltage, and resistance. All right, so that's enough for our introduction, and then we'll get into another example of a series circuit here in the next video, trying to figure out how all that's going to kind of come together. Thanks for